John started out with a BE in civil engineering from University College Dublin, and then he moved to Caltech to undertake a PhD in seismology with a focus on instrumentation, appropriately enough. And then he spent a year as an assistant professor in Puerto Rico before moving back to Europe and to ETH. So John, we're very much looking forward to hearing about this intriguing topic of MarsQuakes. So over to you, John. Thank you.
Thanks very much, Chris, for the lovely introduction. First unstable connection, so hopefully it'll go well. I do have a really exciting topic to talk about tonight. I've been really lucky in the last 5 years to get involved in this InSight mission to Mars, the first mission that's actually recorded seismograms of high quality on an extraterrestrial planet. This project is a huge project. It's managed by NASA JPL. I work in a large team at ETH, and it's really a truly international project. Most of the science payload here is actually developed in Europe, so it's really an international project. I have hundreds of co-authors. I can't even hope to mention them, but really it's a pleasure to give this talk on behalf of my team. I'm going to start with where Chris alluded to in his talk, that getting to Mars is hard. Since the 1960s, there have been over 40 attempts, basically one a year, to send a spacecraft to Mars. A lot of these failed in the first half of this 40-year period. But since then, success has been much more steady. Notable missions I want to highlight are the Viking missions. I don't know if you can see my cursor, but Viking was a successful US mission, the first time a lander actually reached the surface. And both of these missions actually made it. Since then, in the 1990s, there was a couple of missions that the first rover landed, the Phoenix, Spirit and Opportunity. And then in the next 2 decades, there was actually a range of successful missions from NASA to land on the planet. InSight is the most recent of these missions. InSight landed 2 years ago. And in the last window that opened up 6 months ago, there's basically an open window to have a rather fast transit to Mars, opens up every 2 years. And 3 missions launched this summer. You're probably all aware of them, and they're halfway there now. They should land in February. At the moment, there are 6 satellites orbiting Mars. This is really important for us because it's these satellites that actually enable us to get data back from the planet. We're actually at the stage now where every day I get an email that a data package has arrived that basically has the previous 12 hours data. So I'm looking at data from Mars in a very similar way to how I look at data from my own network in Switzerland, which is absolutely remarkable. What I showed you before was missions to Mars. Most of these missions, though, have different goals. Very, very few space missions have geophysics as the primary goal, like InSight does. Seismometers historically have been expensive. They're between 5 to 15 kilos a piece. So this is extremely heavy, and people are and space agencies are very, very reluctant to put such heavy equipment on other planets. Viking landed in 1976. It had 2 seismometers in each of the landers. One of the landers failed. The other one, the picture of it is shown here, and you can see it's very, very different to what I'm going to show you later. But the seismometer was on top of this lander. It never moved off it. So basically, it measured the Martian winds. As I'm going to show you, they're pretty damn hectic. 20 years later, there was a mission that had a seismometer that's very similar to the one that's actually landed today. It's a predecessor of it. It was a French mission. And this had 2 seismometers on board. Unfortunately, this didn't make it outside of Earth orbit. In 2011, nearly 15 years later, NASA selected a geophysical mission, which eventually got called InSight and did launch 2 years ago and landed almost 2 years to the day. The missions we've looked at before have really focused on surface geology, the search for life, and understanding the atmosphere. No mission has really answered any question about the truly deep inside of the planet, and answered important questions about how Mars formed and Mars evolved. These are important to us because even though we know our own planet extremely well, we don't really understand how the other rocky planets formed. And one of the reasons that this is because Earth is extremely active. It has very active plate tectonics. There is recycling, there's volcanoes there. So basically the entire surface, the entire crust is recycling on a millennial scales. Basically we've lost the history of how our planet was in the early years after the Big Bang. We know that Mars is going to, if we can understand Mars, we will get a lot more insight into how rocky planets started at the dawn of the solar system. We know our own planet well. We have over 100 years of seismology and even more of geology. We know the moon relatively well. We have about a decade of seismic measurements there from the Apollo Lunar missions in the 1970s, and we've also returned rock samples. We know that Earth is warm, it's active. We know the moon is cold and it's quiet. There's very little seismic activity. Mars is going to be somewhere in between. Mars is the Goldilocks planet. It's big enough to have had a very active history, but it's small enough to have lost its early heat and frozen and really cemented in the imprints of those early parts of the solar system history. We know Earth well. We've really got 3D knowledge of how the structure is. We know where the discontinuities are. We know extremely well the entire inner structure. The moon we know pretty well too from our 2 decades, but for the Mars, we kind of know that there's we know that there's a crust. We know that there's a mantle that's a certain thickness. We know that there's a core, but we don't even know if the core is solid or liquid. These are really fundamental and basic questions that InSight is going to help us answer. InSight has 3 main packages, three main scientific packages that are going to help answer these questions. We're going to understand the structure of the planet from the seismometer. From the heat flow experiment, we're going to understand the temperature. And from a geodetic experiment, we're going to understand how the planet rotates and wobbles. I'm just going to go into a bit more detail about the science goals. We want to understand the size of the core, its composition as well as its state, the thickness and the structure of its crust, the structure of the mantle as well as its composition, and also how warm the interior is and how much heat is flowing out. We can't answer these questions directly. We need to take direct measurements and infer this information. InSight is going to allow us to measure the seismic activity of Mars and where the seismic activity is located, as well as and from this information we understand the structure. If we're lucky, we'll also see how Mars reacts to meteorite impacts. Now, meteorite impacts are extremely important to us in this project because meteorite impacts can be actually located with high precision from satellite imagery. So we have a ground truth. So no longer do we have uncertainty in location like we have for a Marsquake, but if we know where the meteorite is, we know really well and we can better understand the seismic signature. We also know that we're going to measure the surface of Mars, how it flexes as its Phobos moon passes overhead. We'll also measure the spin rate and wobble, as well as the temperature profile. All of these interact with our science goals, and the direct tools that we're going to use to measure these are SEIS, RISE, and HP3. I want to mention quickly, it's a very common question, is what is causing seismic signals on Mars? We do know that Marsquakes exist. We know now that they exist, but what's producing them? Mars is not active, there's no plate tectonics, but it is a cooling planet. It was in the past extremely hot. It had rampant volcanism. The volcanism is ceased for a long time, but there's still the remnant heat that continues cooling, continues causing stresses. There's also a network of faults across the planet that have been mapped, allowing us to predict how many earthquakes or Marsquakes we expect to see. So we do know that Marsquakes are expected, and there's good reasons why they're actually occurring. We know that meteorite impacts are also a very rich source of signal, and this is an example in the bottom corner where you see a before and after picture from 2008 where a satellite image is taken, and then a few months later a similar snap is taken, and there's a very clear signature of a meteorite impact on the Martian soil. We do know the moon is also going to cause a seismic signature, as well as the atmosphere, and to be honest, the atmosphere is the main signal we currently see. So this is the layout of the mission as it should have been, as it would have been deployed if everything had gone perfectly. We have the SEIS instrument that's lifted from the lander and placed onto the surface of the ground. Beside it, the HB cubed instrument is also lifted from the lander, placed on the ground, and then this little probe is supposed to have dug itself in to a depth of 5 meters, so that it's far below the surface of the ground. It's outside of the influence of the diurnal temperature change, and then it just sits there and records how the temperature changes, and it records the heat flux of the planet. On the actual lander, we have 2 antennas, which are the RISE experiment, the geodetic experiment. This experiment allows us to locate the lander to a precision of a millimeter. And over time, if we keep measuring the location with respect to the Earth, we can measure the wobble of the planet. And this tells us an awful lot about the deep internal structure. We have a UHF antenna, which is used for communication from the lander to the satellites, which then send the message back to us on Earth, send the data back to us on Earth via the Deep Space Network. There is also a full weather station with temperature, pressure, and wind. And we have 2 other important features. We have the robot arm, which lifts things down, but this crucially also has a camera, and it also has a little shovel, which has come in extremely handy, as you'll see. There's also a second camera on the bottom, which is fixed, and it just takes photos with the same field of view, but it has a very carefully chosen field of view. It's got the workspace in front of us. So I'm going to focus first on SEIS and show you what SEIS is composed of. SEIS is actually composed of 2 seismometers. One of them is for the seismologists in the audience, basically similar to an STS-1, which is the state-of-the-art seismometer that was built in the 1980s and still hasn't really been improved. This is a really broadband sensor. The sensor that we placed on Mars is actually achieving better signals, as I'll show you later, than we would ever hope to see on Earth. In addition to this, this is a very heavy and bulky device and needs to be inside a vacuum. The vacuum is shown on the bottom. We have a second seismometer, which we call the short period seismometer. It's a MEMS accelerometer, but it's actually extremely broadband, and it has a much higher dynamic range than any similar seismometer you see on Earth. This is the future of planetary seismology. This device is really cheap, relatively cheap. It's really small. It's really light. It can be placed on any lander or on any system that's traveling onto a rocky planet in future. Together, the seismometer is capable of measuring displacement smaller than a hydrogen atom. It's really impressive. That's not the end of the seismometer though. Because Mars has a very harsh environment, we need a hell of a lot of insulation to protect the seismometer from the environment and actually achieve the low noise that we aim to get. First of all, around the sensor, around the evacuated sphere, we have this insulating enclosure. You'll see photos of this later. On the top of this is this little knob, which is used first of all to lift it off, but this is actually a sundial as well. When we put the seismometer on the surface, we looked at shadows cast by this along this carefully marked plate here, and we were able to determine the true north to accuracy of about 1 degree, which is pretty similar to what we achieve here on Earth with being right in front of a seismometer. On top of that though, this isn't enough to fully reduce the noise. We have a wind and thermal shield, which is placed over this, which really protects the seismometer from the temperature effects and the heavy afternoon winds. All of this is connected using a tether back to the spacecraft to the electronics box, which actually takes the analog signal, digitizes it, and packs it ready to be sent back to Earth. Moving on to the mission timeline, just to give you an overview of where we went. The spacecraft took about 10 years to be built. It's actually an extremely cheap mission. It's basically using the spare parts from the Phoenix lander from 2008. Most of the spacecraft is just spare parts. You can see on top of this, we have the thermal shield, the seismometer, and you can see for scale that this is actually a pretty big beast. It's 6 meters in diameter, and if you stand up beside it, it's rather impressive and surprisingly large. All of this was packed in the very top of this rocket, which was launched in May 2018. I was there with my family. It launched from California at 4 a.m. in the morning, and it looks damn exciting, but actually all we saw was fog. It was a bit of a damp squib, but it was wonderful to be there with the rest of the science team for the launch. The cruise takes about 6 months. We approached Mars in November, doing the last maneuvers to make sure we hit the right spot. And then we had our 7 minutes of terror that NASA like to call the landing that gets huge amount of media coverage, where we take a number of extremely complicated and risky maneuvers to decelerate until finally we land with retro rockets thrusting us up to slow us down. And as soon as we land, we unfurl the solar panels and we check that everything's okay. Basically, the mission was supposed to last for a Martian year. We've just passed that landmark. A Martian year is about 2 Earth years. We just passed that landmark a couple of weeks ago. We are heading into now the extended mission. Everything looks basically okay. We hope that this mission can continue for the next couple of years and maybe into the next decade. It's important to note, though, that when we landed, we didn't start. It took quite a long time to actually check out everything and to deploy everything. This is where we landed on this beautiful map of Mars. We landed, those of you familiar with Mars will be familiar with the dichotomy, where the lower hemisphere is at a much higher altitude to the northern hemisphere. We're just on the northern part of the dichotomy. We're at 5 degrees north. Here we are. We are in a place called Elysium Planitia. That's just south of Elysium Mons, one of the largest volcanoes on the planet, and we're quite close to a number of other spacecraft. The landing site was very, very carefully selected. After 2 years of planning, the site was actually selected, and this was the landing ellipse that was selected. Now, NASA know that they are good at landing, but they're not perfect. So they have an error ellipse of 130 kilometers in length and 30 kilometers in width. And they pretty much guarantee that they'll land there, but they're not sure where. We were lucky enough that we landed bang in the middle. This landing place was chosen in the most boring place of the whole planet because we knew we needed to have a completely flat environment. We needed very little chance of falling into a crevice or onto the edge of a large recent crater. This is one of the first pictures we took, and I remember this like it was yesterday. It still makes me smile when I see these photos. This is the camera on the stowed arm, and when we lifted it up, we took the first picture of the solar panels, and then we started taking pictures of the entire environment, which you see on the bottom, and that's basically a panorama. We succeeded. We landed in the most boring place there is. There's no hill, a couple of rocks. We actually landed in a tiny crater that's about 20 kilometers. It's an ancient impact crater that has since filled with sand. We did a great job of finding the landing site. After we unstowed, we put the arm up and took selfies. This is the first selfie. You can see everything looks good. Everything's clean. We have the seismometer, the shield on top of it, and HP cubed. Now, once we began to think everything worked, we began to deploy. Now, I exaggerated a little bit when I said the previous picture was the first picture. This was actually the first picture. This is taken from the instrument context camera, which is just looking at the workspace in front of us. And there's actually a rather scary amount of dust here. There was a little bit of panic, but in effect, the dust fell off quickly. I'm showing you here a composite of the first 100 days photos taken by that camera. First of all, after about 20 sols, we dropped the camera onto the surface. This is now the first time that we actually have a seismometer on Mars. Before then, we didn't. The seismometer is attached with a cable, and we spent about 2 months playing around with this cable. We dropped everything to the ground, then we started trying to pull it and tug it to make sure that, that it was taut and there was no residual stresses that were going to leak into the seismometer later. You will see that we just got a nice little tug on it, pulled it slightly further back. Then when we're happy with this, then finally we put the WTS over. Now finally we have a seismometer. You see now that the skin drops onto it. It's now coupled nicely to the ground, and now we have a really quiet site. At this stage, the seismometer was leveled and calibrated, but then it was done. The rest of the project, we were just supposed to now wait for as long as possible and record MarsQuakes. Beside it, the HP cubed was popped down beside it, and then you just saw there, that's when we first started hammering. The hammering was supposed to take a couple of days and get us down to 5 meters. But if you know anything about InSight, you probably know that there was problems with the HP cubed experiment. basically the mole failed to dig to anything like the expected depth. This is the picture taken from the camera that's on the robot arm looking directly down onto the HP cube frame. And you can see that during the first hammering session, what actually happened was the frame shifted completely unexpectedly. And we've known, because we can actually tell how far, there's a little counter there that lets us see how deep the mole has dug, that we were only about 30 or 40 centimeters in. We decided then to see what the hell was happening. We lifted up the frame completely unexpectedly. We had never expected to have to do this. And we spotted that we now had a situation that the bouncing around had basically created an empty pit around the mole, which was now at quite an angle. It took a long time to figure out the next steps, but we decided that we would leave the frame out and we would try and use the shovel to pin the seismometer, or to pin the mole down and try and add additional friction so it would actually dig. We did this really successfully until this happened. This is what we call the backing out phase, where the mole, instead of digging, all of a sudden backed out about half of its length and was sticking out of the planet. This was rather bad PR, unfortunately, for the project. People forgot that we had a seismometer beside it that was working brilliantly, and were focusing on the fact that they were seeing photos every day of this unfortunate mole. It's been slow work. We've managed to use that shovel that was never supposed to be used to pin the mass down, to pin the mole down, to push it down, to continue digging. And when we got down flush with the ground very, very recently, in the last few days, we've dug with the shovel. We're doing soil mechanics completely unexpectedly, and we've filled the soil up. We hope that this will increase the amount of friction against the mole, and we'll probably pin down again with the shovel and hope that we'll finally get a little bit of depth for the seismometer, or for the mole. It's really important that the mole can get down as far as possible if we're to salvage any signs from the mole. I'm going to move on now to other parts of the project. InSight is effectively the first time we've ever had a weather station. Other Mars missions have only been on when they are collecting data, which is periodically. So we would, even though they had weather information, it was only partial. It was a half an hour a day or something like that. Because we have a seismometer and the seismometer is always on, we have the opportunity here to have a full weather station too. And this is really important because weather is the driving signal we see on our seismic data. The weather on Mars is pretty grim. At the moment, we're moving towards winter, and we're now seeing temperatures. Sorry, this is in Fahrenheit, but basically from about -20 to -100 every day. But there's a massive temperature swing. If we stack all of this from across the project, we have basically the first time we have a full climate record from any spot in Mars. I'm not going to go into this in detail, but on the top here we have the air temperature, and you can see, because we're quite close to the equator, we don't have a lot of flux. We see this variation of about 80 degrees pretty constantly throughout the year. We also have pressure, wind speed. The wind speeds are dramatic. They go up to 20 meters per second every single day. But they do quieten down at night. We also see the wind direction as well as the opacity. I'm going to move on and show for the first time some seismic data. This is a 24-hour window. I'm going to start talking in sols now, because on Mars we don't use Earth days, we use the Martian sol, which is slightly longer than an Earth day. It's 41 minutes longer. So for the project, even though the data comes down to us in Earth time, when you're analyzing it, it's better to actually use the Martian time, so you have the local time on the planet rather than something irrelevant on Earth, which is shifting by 40 minutes every day. The waveform for this 24-hour period is shown in the top, and this is in acceleration. You can see a really regular pattern that we start off with low amplitudes that rise into an almighty mess in the afternoon. And then towards the end of the afternoon, they calm down till we get a really quiet period. And then in the late afternoon, it gets a little bit noisier again. Seismologists, though, are very used to looking at data in what we call spectrograms. So we combine the time domain with also the frequency domain. So we can see over time what frequencies are being excited. We're looking here now from 50 seconds, which is a very long period, up past about 1 second. Around here is where on Earth we would see waves from the ocean. and then higher frequency at about 10 hertz. Now we're beginning to get into something like the energy of a car or a train passing by. So you really, by looking at the spectrogram, a trained seismologist is much more able to identify signals that are spurious, that are unusual, and likely to be caused by seismic energy rather than typical behavior of the seismometer. So there's a couple of obvious features. These spikes we see here are very broadband. These are glitches. Unfortunately, the seismometer is susceptible to mechanical spikes and offsets because the temperature change is so strong, despite the insulation we have. Another primary feature are these horizontal lines, and these are extremely important. They turned out to be extremely important for our project. The first is a 2.4 hertz resonance. So this is a broad resonance we see only when it's quiet. It's not excited by the winds. When the wind actually comes in the afternoon, it disappears. And most importantly, it is excited by MarsQuakes. On top of that, a little bit higher, we have a suite of much more narrow modes. These are actually caused by the vibrations of the lander, which is still only 1.5 meters away. So as this vibrates, it couples into our seismic signal. These now are strongly excited by the wind. They disappear when it's really, really quiet because they're not being excited. And the frequency is modulated by temperature. It's dropping when the temperature is hot, which is a clear signal of something that's responding to temperature effects, like you would expect by something in the sunshine on Mars. Crucially, seismic events do not excite any of these modes. And I wonder if you've noticed, but on this particular day, there are 2 beautiful MarsQuakes that have been identified by our team. This is early on in the project. These were one of the earliest MarsQuakes. I'm going to show you a second day where you'll see exactly the same features, but I'm going to highlight a very different type of MarsQuake, a much higher frequency. The ones we saw before had energy down here. This one has energy going from 2 hertz, including the 2.4 hertz, right up to the Nyquist of our signal, which is 20 samples per second. We are capable of getting higher frequency data down on demand up to 50 hertz. So you've seen, I forgot to mention that the color here is telling you the range. Yellow is really noisy and blue is really, really cold. You're going to see this again and again in the next figures. This figure here is probably very much for the seismologists in the audience. It's a little tricky to explain, but it's basically showing us the lowest resolution our seismometer is attaining. This is a PDF of a PSD, which just sounds like jargon. I apologize for that. But basically, if you track the red color here, you're seeing the lowest noise that we're seeing on Mars in any particular day. The other lines here are actually lines from other signals we've seen in other places. Most important, let's look at here first. The red line here is what we saw when we were on the deck. The noise on the deck, this is a log scale here, was orders of magnitude higher to what we saw when we put the seismometer down. We would not have seen anything at all if we had kept the seismometer on the lander. We had no chance to hit the resolution we're seeing by just taking that simple move of moving the seismometer 2 meters away. Another really important signal to see is this dotted line here, which is tricky to see, but it basically tracks here. This is the low Earth model. This is the lowest noise that we ever see on Earth. What this is actually telling us is that the noise on Earth is much, much higher than the signal that we're actually seeing on Mars, up to about 5 hertz when they begin to get similar. At between 1 and 10 seconds, which is where we see most of the energy from teleseismic earthquakes and MarsQuakes, are where we expect it to see, we are 3 orders of magnitude better than anywhere we've ever seen on Earth. The moon is shown by these white lines, and by these white lines, so we are actually very, very similar. We're much, much better than the moon at longer periods, and at about 5 seconds, we're pretty much the same. Moon was slightly better, but basically it's extremely fair to say that what we're recording on Mars is the quietest seismic station in our solar system. It's really awesome. I'm going to show you similar information tracking the noise across the project. This first figure here basically is showing us what happens when we first landed to when we put the seismometer on the ground. So it's tracking that 3 orders of magnitude drop again. In this figure here, red is noisy and blue is quiet. And this is the data we collected after day 4 when we first turned the seismometer on. After day 22, we put the seismometer on the ground and things started getting a lot better. Then we started playing with the tether, we started releasing stresses, and finally we put the WTS on. And when we had this on, we were able to finally record for 24 hours because we weren't worried that we would risk the integrity of the seismometer by having it working at minus 100 degrees. At this stage, we began to get much more high quality data, and this is when we started doing what we call the science phase. This next figure is basically the same again, except it's showing the VBB with a different color scale, but now it's moving from Sol 80 once we put the hat on to where we are basically yesterday. Today we're Sol 703, and this was from a few days ago. This is basically tracking the noise every day from that spectrogram, every day, just one after the other. And so we get a really nice composite image of how the seismometer noise is changing over time. The first order feature, though, is that this windy period is in the afternoon. For pretty much most of the project so far, except for the last 200 sols, we had this gorgeous period of time in the late afternoon. And also once in a while, also in the early morning when noise was really quiet. This was our prime time. I'm now going to overlay all of the positions of the MarsQuakes that we've now identified. And you clearly see that when it's nighttime, that's our chance of observing MarsQuakes. We've now seen about 500 events. Almost all of them occur in this narrow window. And basically none of them are large enough to be seen during the heavy winds in the afternoon. This is extremely colorful because us in the Marsquake Service classify the events in different ways, as I'm going to show a little bit later. This is another way of looking at the history of the project so far, going from Sol, from about Sol 50 up to today. This is looking at the amplitude of the background noise. So this line here shown at the top of the gray is basically the quietest amplitude of any particular day, and in black is the noisiest amplitude. So as you can see at the start of the project, we had very little range and everything was pretty noisy. Then we got to a stage where the afternoons were really quiet for a long period of time. The evenings were quiet, the afternoons were terrible, but they were only for a couple of hours. So we had this window where we were seeing lots and lots of events. Since then, the range has gone back up where we're basically windy the whole time of day. We're not getting any break where we're actually able to see MarsQuakes. Now there's two different plots here. The top one is showing a longer period energy, and the bottom one is showing the 2.4 hertz energy. And we've classified events as either being long period or high frequency, exciting the 2.4 hertz. You'll also see that the MarsQuakes are shown here in amplitude and time. So you see exactly the time that they occur as well as the amplitude they had. Almost all of them are so small that they'd never be seen, except for one or two of them that you wouldn't have a hope of seeing them during the noisiest part of the day for both classifications. We're really only seeing small events, and we're only able to see them because of the quality of the seismometer and the fact that, that the winds do die down for periods of the year. One last figure is that's not the only event that we've been tracking. Like on the moon, we also believe that we're seeing thermal events. Thermal events are very short, high frequency spurts of energy that occur at particular times. On the moon, because sunrise and sunset take so long, you would see clusters of these around those days when you're having the sunrise and sunset. On Mars, we see them also occurring predominantly just around sunset, but with some slightly more complicated behaviors. We believe that these are rocks in the vicinity of the lander cracking. We're very excited to see if next year, when we get back to the same phase in a few months of the Martian year, whether we see these patterns emerging again. Looking more particularly at MarsQuakes, this composite on the bottom kind of shows you highlights of MarsQuakes in the spectrogram. So you're seeing the same frequency range, and you're just seeing the pulses of energy at different days for each of the different MarsQuakes. We have 500 events. The key characteristics is that we are actually able to identify P and S phases. So we are able to see impulsive energy, and we are able to infer what type of energy it is and use it for seismological investigation. One thing that is important to mention is that initially there's been no clear identification of surface waves, of depth phases or reflected phases. So this means that the amount of information we can actually glean is rather limited compared to what you could do with conventional seismic events that you get on Earth. These are long duration events. All of these images I've shown you so far are 24-hour spectrograms, and we're seeing them. They have durations of 10 to 20 minutes typically, and sometimes up to an hour. Again, the amplitudes are tiny, and so are the magnitudes. We estimate that we're looking at, on a planetary scale, events from magnitude 1 to magnitude 4. We haven't seen anything higher than that. So we've been surprised by the lack of larger events. Events are classified by their frequency content, since we still don't unambiguously understand their source. There's still a long way to go here. We don't label them by their source, but more by their frequency content. So we have a low frequency and a high frequency family. I'm going to talk a little bit about how we locate the earthquakes, and this is my bread and butter. This is my role in the project. I'm managing the team that does, the international team that does this. We look through all of the data collected. We take turns looking at it every single day. Once we see something, we sit together, we detect, locate, and characterize everything, and we manage the catalog, which is released to regular seismological catalog providers. I know it's obvious, but I just want to reiterate what we're trying to do here. We have, on Mars, we have a single seismometer. On Earth, by comparison, we have thousands, tens of thousands. This figure here shows you just a snapshot from what we have just alone in Europe, and in my network in Switzerland, we have about 200 sensors. So what we do in Europe is so different to what we do on Earth today is so different from what we do in terms of locating earthquakes on Mars. It's really quite hard to even compare what the approaches are. Basically, we're going back to a century ago when seismometers on Earth were extremely rare. We only had one or two. We had no timing. We had no timing between sensors. So basically, we would look at a seismogram from one record and try and interpret where it was. We spent a long time coming up with trying to brainstorm how we could best locate events. We came up with this approach here, where we would look at both surface waves. We believed that Mars would provide us with magnitude 5s that would be able to excite surface waves that would travel around the planet multiple times. This is something that we only see rarely on Earth, but because of the noise that we expected to see, we thought it was liable that we'd see it on Mars. We haven't been so lucky. More importantly, we also invested time in looking at body and surface waves, body and surface wave picks, just looking at PNS waves, and this has proved a lot more fruitful. But we did develop a location procedure that would allow us to compare anything. So if we're lucky enough to see big events in future, we will still be able to use these methodologies that we invested heavily in doing. Sometimes different planets surprise you. So this is what the time series of probably the best event we have, which we call Sol 235b. So it was the second event we saw on this particular Sol. This is a lovely signal. You have a really clear impulsive P, you have a slightly complex S. These are polarized signals, but it's very easy to pick them. Polarization, you can determine the back azimuth by seeing where the energy comes from different phases, and you can infer then that the earthquake must have come from a particular direction. Importantly, if you're able to identify phases, you know the time difference between them. And if you know a velocity model for the planet, you can guess with that time difference how far away you actually are from the epicenter. So with the time difference as well as the back azimuth, you're able to combine those and get a unique location. We've only been able to do this for 3 events of the 500 we've seen, unfortunately. How do Marsquakes actually compare in terms of their time series to what we see on the Earth and the Moon? This figure was extremely popular around the project at the very start when we saw the first events, just to really give us some context about how different what we were looking at is. This is an earthquake recorded really close to my house here in Switzerland from a local magnitude 4. So this is something that we would never see on Mars because we landed in such a boring place. This second one here is an earthquake in the Jan Mayen Islands, which is a similar distance to the Marsquake. And you can see that it's really quite different to our Marsquake. Our Marsquake is much more chaotic. It looks much more scattered. Even though we can identify phases, we don't identify too much else. A moonquake, in contrast, is even more scattered. This is actually quite a local moonquake. It's only 500 kilometers distance, but its duration is over an hour. The scattering on the moon is such that all the energy just bounds around, and events there, once the moon starts, it rings like a bell. Mars, our first interpretation, was somewhere quite in between. Also shown here is the amplitudes. So for a moderately sized earthquake on Earth, we were seeing 1,000 times smaller for the largest event we were seeing on Mars, just giving you, again, a scale of the difference in magnitudes. We got a bit more clever, though. We began to look a bit more closely at really how different these were for very, very similar events on Earth compared to Mars. So on top is a broadband record of our best Marsquake. And on the bottom are 2 earthquakes recorded in Switzerland at almost exactly the same distance. The first one is in Greece. It's relatively shallow at 70 Ks, and the second one is just underneath Gibraltar. It's a very deep earthquake at 600 kilometers. It's in the mantle. First off, they don't look that similar. These events, even the deep earthquakes, are full of long period energy, and the top one is full of surface waves. It's not what we see on Mars. Although if we high pass the filter, though, and we throw out all of that low frequency energy that we're just not seeing on Mars for some reason, we do see something that's actually extremely encouraging. The deep earthquake on Earth looks remarkably similar to the Marsquake, the best Marsquake we have. When we realized this, we got great encouragement that we could actually start trying to interpret some of the noise, that some of the signals here that we thought were too complicated and were full of scattered energy, but actually on Earth, we'd be able to interpret these signals here. So why can't we do it on Mars? So once we saw this, it really changed our approach to how we tackled the complexity of the seismic signal we were seeing on Mars. That was for the best earthquakes, or for the best Marsquakes. Anybody who's familiar with seismic energy or seismic data knows that for every one nice event, you get 10 smaller ones and 10 magnitude and 10 another magnitude unit smaller again. So we were seeing an awful lot of tiny events and only a few nice ones. We did spend a lot of time trying to match waveforms. We not looking at the raw waveforms, but turning them into envelopes and comparing envelopes to see if we could cluster events. And through this, we were able to actually provide distances for way more than just a handful of really, really nice events. Once we have distances, we can compute magnitudes. And this figure here shows us the magnitude distance range that we've actually got now on the planet. On the top here are the LF family, the longer period ones. And these are ranging from about magnitude 2.5 down to 4. And they do cluster in two different distance ranges, one at around 30 to 40 degrees and another around 90 to 100 degrees, suggesting that there might be particularly active parts of the planet and other places that are less active, just like we'd see on Earth. For the high frequency events, they're much, much smaller still. But they do seem to cluster much, much closer to the lander. It's important to note that we see none of these longer period events close to the lander at all. 25 degrees is about as close as we've come. If we actually put these on a map of Earth, on a map of Mars, if you have a list of earthquakes, the first thing you do on Earth is plot them and illuminate where seismicity is occurring. It hasn't proved quite so easy to do this on Mars because we've only been able to locate 3 events, but here they are. This is our sensor. This is Elysium Mons, the giant volcano at about 20-25 degrees away. And these are our 2 located events and a third event, which has a less reliable location. It's really interesting to see that all 3 events we have so far have a similar back azimuth. And if we look a bit more closely at the geology, these are associated with a structure, a rifting structure, a graben structure called Cerberus fossae. And we have been able to also look at focal mechanisms, which do suggest that there's also opening here. So everything we're seeing is quite consistent with these being associated with the geological structure we're able to see on the surface. These other bands in the map here show the other event clusters we see for the other event types. it's important to note that we're seeing very, very little at distance, and we're really not seeing any events from the volcanic province of Tarsus that we expected would be the richest source for seismic sources. So in terms of interpretation, this is where we are. The longer period events we believe are occurring in the mantle at depth. Their waves are propagating only in the mantle, and they're not producing any high frequency content. In contrast, we think we're also seeing events that are actually located inside the crust. These are not managing to produce deep, longer period energy at all. So they only have high frequency waves that are reverberating in the crust, arriving to our lander. It does appear that most of these events are probably coming from the southern hemisphere. In terms of earthquake rates, we have seen that Mars is more active than the moon. This is the line for the moon on the bottom here, and on the top we have a global line. So this is what we'd see on Earth when we take into account plate tectonics, and this is what we see in the moon, which has no plate tectonics and is extremely cold and barren. And on Mars we expected something around here. We observe here, but as I showed you before, what we detect is quite different to the real rate of seismicity on the planet, because we can only see earthquakes in the quiet time of day, and we can only see them from close by. So we need to account for the fact that we have a very limited visibility and push up the range which falls between these bounds here. So we do know that that Mars now is quite clearly a couple of orders of magnitude more active than the moon, but it's nowhere near what we see on Earth. It's much closer to a region of the Earth in the absence of plate tectonics, such as the east coast of the US. It is important to note, though, that we have a depletion of higher magnitude events. We would expect a rather straighter line here, but unfortunately, we just aren't seeing the larger magnitude events here, which is probably at this stage, it's a persistent feature. It's not just because we haven't seen enough data, but with our second year of data, this should get stronger and stronger. I'm almost finished now. I just want to show highlights of where we're going. We've done the easy stuff. We now start trying to dig into the seismic signals a little bit deeper and try and understand everything. We're now going for secondary phases and looking if we can see double P and double S and triple S. So basically waves that are basically, that basically instead of going directly through the structure of the planet are bouncing off the crust and going down again. We've been quite successful here. Once we start identifying these secondary phases, we actually begin to get much more it becomes much more plausible for us to provide more high quality structural models of the upper mantle and really understand the true speeds of the different layers in the planet. One of the other key goals of the project is to look at the core radius. And we have two independent ways that we're searching for this. We also believe in the seismic signal it's possible to identify a crustal reflection. These are really tricky. We need a lot of events. They need to be close by. We need to get convinced that we're actually truly seeing this crustal reflection, which is a very, very small signal. Independently, the geodetic experiment is maturing. It's seen a year of data now, and they also are beginning to collect data that is conclusively telling us the size of the Martian core. So in conclusions, the project is going great. SEIS is working well. The planet is active. We have pretty much an event a day. We're seeing events in two different families. Some of them are traveling deep. Some of them are traveling shallow in the crust. We're getting evidence for all different hosts of cool features in the planet, but there's still so much more to go. Just one note of caution, this picture is taken from the same view, but at different days of the project. This is basically from day one. We had just beautiful, crystal clear, everything was gorgeous. About half a year later, we're now full of dust. And now we have a thick layer of dust. We're losing power. We're losing the ability to generate solar power slowly but surely, and we're also we were initially extremely hopeful that we would see dust devils. We do see dust devils in the seismic data, but none of them are hitting the solar panels and cleaning them. So what we hope is going to happen is that sometime we will get a decent blast of wind that'll shake the dust off and get our power back up to high levels again. Finally, everything I've shown here has been published pretty much in the last 9 months. And the list of all the papers is here. There's even a special issue, a special section in Nature Geoscience showing the key results. So I invite any of you interested to take a look there. With that, I'm finished. I'd be very happy to take questions. Thank you.
Thank you very much, John. Absolutely astonishing stuff. It's such a great collaboration between engineering and science. I know on Earth, we always want to put out more and more sensors, but you don't have that choice, and you have to really, really squeeze it to get some good science out of what is already just astonishing engineering. It really enjoyed your talk. So we have a lot of questions. I'm not sure I'm going to get through them all. And as I was trying to listen to the talk, I probably haven't managed to cluster all the questions into some sort of meaningful thematic structure. But I will actually start with one that came in just right at the end there. And there was a question about dust devils, and you mentioned dust devils, and the question is, what do dust devils look like on the seismic data? They haven't come across the lander to clean it off, but what do they actually look like on seismic?
That's a great question, and I don't have a slide for it, unfortunately. I have a few spare slides. I don't think I have one of what the seismic signature looks like. Let me. I actually have a cool picture of a dust devil from the Spirit rover that was taken. So we know that they exist. They have a clear seismic signature. We have a pressure sensor there. The pressure sensor shows a clear drop, and at the same time, the seismic signal is jumping. It's a really rich signal, but key to let us know that it's really a dust devil is that there's a long period tilt. You see if the seismometer is here, you'll see as the dust devil comes by, it tilts in one direction, and then the ground tilts the other direction as it passes by. We're seeing these every day. It was actually the first thing we saw when we landed was, oh, dust devils. We have more dust devils here than have ever been observed before anywhere else. We're breaking records for dust devils.
Absolutely fantastic. A question about you mentioned that you're seeing a lot of action in the atmosphere, and there's a question: will the seismometer pick up the incoming Perseverance and the Chinese Taiwan landers in February 2021? Do you expect to see these coming through based on what they do to the atmosphere?
No, the science team has a paper coming out on this. It should be submitted in a couple of days. The short answer is it's too far away. And if the landing is gentle as expected, we are unlikely to see it. We've done a careful analysis. It's basically 80 degrees away. It's far. We wouldn't see we would need a really big signal to see something at that distance. It's also unfortunately planned to come in during daylight hours when we know our seismometer is measuring wind. So we're in double trouble here. The signal will be too weak and our seismometer is noisy at the time. Unfortunately, we don't know where the Chinese lander is going to land. It's possible we'll see it, but we can't confirm yet because they haven't announced. I'm not sure they've decided where, at least publicly announced where the landing site is going to be.
Okay, great. So there's another question, somebody with their engineering spectacles on. So they're asking about launch and transit, and about how you protect the seismometer from a pretty rough start when it's launching. Is it somehow clamped, or how is that protected?
Oh, it's locked. It's locked really tight with I forget, they're called frangibolts. That are released by putting a current that warms it up and then just releases it. So when we're ready to release things, we just send all these currents through them, and all the frangibolts unlock, and we loosen everything. But it's a good question about what happened on transit. Actually, the SP seismometer, the MEMS, was turned on. It was an accelerometer, so it's able to handle these stresses. We actually measured it during cruise. And actually the first time anybody has taken a seismic reading from data in deep space.
Okay. And with the MEMS, did you get down to the noise level on the instrument in cruise, or did it?
Yeah.
Yeah.
That's how we know the noise level, because we got it on cruise.
Okay, very good. So a question then about, I think you touched on it a little bit, but the seasonality of what you see. I guess you don't have enough seasons to understand that yet, I presume. But the question is, do you see some seasonal effects, or can you hint at some seasonal effects at this stage?
For the seismicity?
Yes.
Yes. Yes, you can. I don't know if I should jump back to that slide, but there are strong suggestions that we're not only seeing noise, but we're also seeing some seasonality, which we don't quite understand. We need to capture another year to see if that's just observational bias, or it's true that, I'll try if I can run to that slide. It's miles away, but let me see if I can zoom back this.
I'm sure we'll be happy to see the other slides as you flick back through them. They're all very exciting.
I think this is the best slide to address that question. This basically shows you the low noise. And so the first thing you see is that the bottom events, sure, we only see them when it's really quiet. But there's a block of events here that are relatively, I don't know if you can see my cursor, there's a block of high amplitude events. And these actually only occur during the time window when it's around here. And yet the noise is actually quiet enough in other times that we should be seeing them there too. So we are fully aware that there is apparent seasonality that we don't yet understand. Certainly for the high frequency events. For the top plot, for the low frequency events that are going through the deep mantle and are probably occurring extremely deep, there doesn't appear to be that level of seasonality.
Okay. Yes, somebody else is really intrigued with the location technique. You know, pointing back, getting a PDS delay time and pointing back. But the question is, how do you know what the velocity model for Mars is in advance? And does that make a big difference?
We actually, it's a bit more complicated than a single velocity model. We use thousands. We use thousands of plausible velocity models, and we sample them all to get a PDF of how far away it is. So we know we don't know the velocity model. That's what we do for these events. Sorry, I'm going to get a little technical again, but that's what we do for the low frequency events that we expected. For these high frequency events at the bottom, which are really high frequency and only going through the crust, we didn't expect to see anything like this. You would never see events like this on Earth that are at teleseismic distances that have no longer period energy at all. So we think we have a solid way of explaining them by basically reflections inside the crust and just energy bouncing, high frequency only energy bouncing inside the crust. But we're not in a position to have sophisticated sets of plausible velocity models. We use a very simple single velocity model for the crust to explain the distance of these events.
Okay.
We need to improve.
And a related maybe an extension of that is there's a question as to how you calculate focal mechanisms, which I guess for the non-experts tell us what sort of faulting there is for the event. How do you do that with such a limited amount of data? Normally one would do that with stations that surround the the faults that you're looking at, but you only have one station. So how do you get that sort of information?
It's a great point. It's analyzing the data extremely carefully, being quite brave about uncertainties in your velocity model, uncertainties in your depth, interpreting signals that are weak. It's hard. Nobody would ever try and do this on Earth, to try and determine the focal mechanism of an event at 30 degrees from a very small earthquake. You just wouldn't need to. Yeah, it's really challenging. And you're making a lot of assumptions, and we've tested the methods we use on Earth and do get reliable results for known earthquakes on Earth, which is how we have some confidence that it makes sense. It's also good that it's consistent with the stress field in the location of the earthquake. So the story is convincing, but it's planetary science, so the uncertainties are much larger than they are on there. It's just much larger uncertainties than we have on Earth. Yeah,
sure. Another question is just asking, could you quickly recap where else do we have these types of observations? So seismic data. So you mentioned the moon, Earth.
We're finished. We're finished. You're finished. We have 6 months of data from the top of a lander from Viking in 1976. We have 10 years from a good number of short period sensors on the moon, and we have the Earth.
Yeah. And just a question for myself, actually. I noticed that the moon, the seismic trace goes on for a very, very long time. On
Yep.
Earth, it goes on for a shorter length of time. And then Mars is intermediate. And I guess that scattering around is in the moon shows that the moon, I guess, is pretty dry because there's not very little absorption. So can we say something about, water on Mars just from the scattering? Is there any information in there to tell us how dry the planet is at depth?
It's not that conclusive yet. There's people working on this. There's people working on attenuation and scattering and trying to eke out as much information as they have. But there's actually quite a lot of disagreement across the science team over which data to interpret. There's not that many events that are high enough quality to really analyze and use this type of tools that are really standard tools we have here on Earth. Just don't work with the type of signals that we've seen. So a lot of people are kind of going back to square one and first principles rather than doing the low-hanging fruit of just applying techniques that have been successful here on Earth. We really had to recalibrate many. It's not just this, but many of our approaches once we saw the data. And we have so many people in the science team that are just waiting for surface waves from magnitude 6s that are scratching their heads as to what to do with this data. It's tricky.
Yeah. We've an interesting question. You mentioned meteorites at the beginning. Have you seen any meteorite impacts so far? Or do you know how often they might occur?
Yeah. We have seen one. We saw one 70 kilometers south of the lander quite soon after we landed. We were super excited. We were sure we would find it. We couldn't find a convincing trace. It was a small impact. It was only 2 meters diameter, maybe two or three, but we still were a little surprised we weren't able to see it. There are satellite images being taken all the time, repeating. So we do know that meteorite impacts are always occurring. But the chances of seeing a large enough impact that has a diameter of on the order of 10 meters that we'd be able to see basically anywhere from our seismometer is pretty much 1 in every 2 years, which is pretty much the duration of our project. So it's touch and go whether we will actually see one during the lifetime of the project. We were more optimistic at the start of the project that meteorite impacts were going to be a really significant part of what we're seeing, but we don't have any events that are sufficiently rare or different for us to say, oh, that's an impact, unfortunately. All the events we're seeing kind of cluster, they kind of repeat. They look like natural seismicity on Earth rather than a once in a blue moon event that an impact is.
Okay, so I'll take a few more questions if you don't mind, John. We have a lot of questions, and I have to say a lot of people are really appreciative of your talk. So that we're getting a lot of excitement here. So one of the questions is: Are you worried about running out of power? And why did the lander not have a little brush for brushing off the solar panels? Why were you guys expecting dust devils to do all that work for you?
Touching the solar panels is quite a no-no. But the experience was with other missions that the power budget was more than sufficient, and cleaning events did happen on other solar powered missions. So the assumption was that something similar was going to happen here. As I mentioned before, dust devils were seen in photographs with previous missions. We have searched, we have done so many photographs. We know we're seeing tens and tens of dust devils a day. We're scanning all the time to see if we can catch one in action. It seems that we're having dust devils in Elysium Planitia without dust. So they're just basically pressure drops, but maybe we won't get the type of activity that's going to scour the solar panels clean. Why we don't clean them? We're not going to at this stage, put it that way. There's no brush.
Leave well enough alone, I guess. Yeah. So we're getting, some people are digging into some of the details, which is great. And of the data that you've presented. So Mars seems to be very quiet soon after sunset, but not before sunrise. Any idea why dusk is quieter than dawn? Do you see that in the data, or maybe it was?
Oh yes, we clearly see that in the data. That's first order. It's a first order effect for most of the first year. That was really what was happening. I'm not a climate scientist, but I do know that no climate scientist involved in the mission was in any way surprised, and it was actually predicted. They actually have been telling us now that the noise was coming, and that they tell us that it's going to be here until February. So those of us looking for Marsquakes are taking a little bit of a break compared to the part of the project where we're seeing 4 or 5 a day, and it was really, really hectic. But I don't have the fact that winds totally drop in the late afternoon and then start picking up around midnight and are quite steady and quite until daybreak. I don't have a good answer for that. Sorry.
Yeah, fair enough. I guess you showed some, just pointed it, you showed some very strong wind speeds, but I guess the atmosphere is so thin that that's why you're not losing your lander to high winds, I presume.
Yeah, the atmosphere is much, much thinner. So we see heavy winds, but they're not quite as dangerous as they would be on Earth.
Okay, so another one, very interesting results. Do you think the mission will reveal key aspects of the planet's internal structure? Are you going to get to that far with this particular mission?
Yeah, we are. About a year ago, when we were first trying to unpack the data, I would have been more pessimistic. I'd say it's a challenge to understand, but we're really beginning to get conclusive results. There's 3 or 4 teams independently trying to analyze the data and go for the same features in the seismic data, the same secondary phases, the SEIS bounces, the surface waves. They're beginning to emerge. Once we have these observations, then we have the keys to allow us to understand better than first order the structure of the planet. Okay,
and so that was the person who asked that question just replied wonderful. So so they're happy with that. So I'll ask a final question. You know, if power is not an issue, how long will the program last before you call it a day?
Something's going to fail. The seismometer can only do a certain number of temperature cycles. There's electronics there. Something is going to fail. So everything that travels to Mars is checked 1 million times. The level of quality control before anything is allowed near a spacecraft is just unbelievable. When you deliver a part, it goes through so many amount of tests, so that the chance of failure is so much lower than you'd have on Earth. But the fact is that these components had a lifetime of 2 years, and we're now beyond that. But on the other side, they have experienced the full Martian climate now. So they've been through a full cycle. They're seeing nothing new in terms of temperature. There's no reason to expect something to fail. And on the other side, you know, the Apollo mission, they basically turned it off after 10 years because they ran out of budget. They couldn't, those seismometers could still have been running. I would be surprised if this mission is turned off for anything other than technical obsolescence.
Yeah.
So
I'm hopeful after all that effort, I think it would be quite a shame to do that.
Yeah, for the sake of... there is no horizon for a second seismometer coming. There are a lot of countries that are doing interesting technical demonstrations that they can travel to Mars. Maybe we'll be able to get a scientific payload on one of these future missions, but it's always hard to get seismometers on the payload.
Okay, and maybe my final question, when are we going to see human boots on Mars and somebody walk up and have a look at your seismometer in person?
I don't know. I don't know. I have no good answer to that, but I'd be very surprised. And you know what? In the Apollo missions, it took the astronauts 5 minutes to deploy and bury the sensors. This time, it took us 3 months. So I really hope that the next time we deploy a seismometer, it's someone lifting it up and burying it.
Very good. And so I'm going to finish with a final comment from Miguel, who's H10, and he just says, excellent. So I think that sums it up, John. Thank you so much for an absolutely gripping presentation. As I say, fantastic engineering, really pushing the science as well with what are some limited data. So we really appreciate it, and I hope that everybody enjoyed it. But judging by the comments, I think you struck a chord. So thank you everybody for joining us tonight. As I say, I hope that you enjoyed the experience. And remember that we are celebrating our 80th anniversary, pandemic and all, and some of our events have been pushed into 2021, but you can follow us on DIAS Eventbrite and or at dias.ie. You can connect in for the newsletter. So I'll just finish by saying thanks very much, John. Best of luck to you and your colleagues in this great work, and we'll be keeping a close eye on your progress. Thank you.
Thank you. It was a real pleasure.
Best to everybody. Bye-bye.
Goodbye.